Okay, the next bit, the Billy Special, as it is known, if we have these leaves here, and we may know that the average length of leaf, and this curve is symmetric, the curve is beautifully symmetric. Say we knew the average length of leaf was 8 centimetres, and here we have the frequency, or the probability is what we're really dealing with here, probability. The probability that a leaf length is 8 centimetres is, Billy? 0.
It pains me to say that.
It pains you to say it, but it's 0. Yeah, remember, Billy is our expert. Probability of it taking any specific value is 0. You will never find a leaf that is exactly 8 centimetres long.
I'm guaranteed to get that wrong in the exam.
You could always, in theory, measure it more and more accurately and find out actually it's 8.00000000001 or something like that.
Billy going out and doing this experiment to find one now.
Billy wants to do that. It's up to Billy.
You're doing like the probability of picking a number, and obviously the probability of picking the number 8 is possible.
Not if you're choosing from all continuous numbers.
Yeah, but it is though. It's definitely possible because number 8 is like bang on.
Yeah, I would have thought it is part of the set of continuous numbers. Yeah, because it is.
But it's one continuous number out of an infinite number of continuous numbers, so the probability would be 1 over infinity, which is 0. So, if you wanted to know the probability that the length of the leaf is 8 centimetres to the nearest centimetre, what are we really talking about there?
7.5 and 8.5.
Yes, we're talking about 7.5 to 8.5 for the length of the leaf. That's the less than sign. Should I put extra equals bits on there?
It doesn't matter.
It doesn't matter. That's again a Billy Special. It doesn't matter because either ends have no probability attached to them. Okay? So if you wanted to know, the length of the leaf is 8 to the nearest centimetre, then you'd do it between 7.5 and 8.5. Right, now, when I did this...
normal distribution.
Sorry?
That's still the normal distribution.
Still the normal distribution,
It's
yeah.
the same as the...
It's continuous random variable? It's a continuous random variable, yeah. It's one of many...
Oh, so the normal distribution is part of this
Yeah, it is a continuous random variable, yeah. Okay? Right, what we're going to do now is we are going to look for at an example, I suppose. I got here that we are going to pretend that we know about all the boys in year 13. Greg, we didn't have any girls in our group last year, did we?
No.
Which is apologies. This is why. Okay, it says boys in year 13. That we know that their mean, and I'm assuming we are talking the heights, is 175 centimetres, and their standard deviation is 6 centimetres. And these are their heights. And I actually think from looking at my notes last year, we actually measured everybody in the group because in the maths room I had a tape measure going on the wall. Can you remember that, Greg?
Yeah.
These can be used in practical maths lessons.
No.
Like go out and do math.
You would have...
I'm not asking myself that, so
So, but in the moment...
This is about things we could throw at walls.
Did he? No, I meant the second motion one where he went to the courts and ran out.
What we're going to do here is we are just going to pretend we have this knowledge. And I will just occasionally use the sort of tongue-in-cheek phrase, the God of statistics has told us that this is true. In real life, you wouldn't know unless you went round and measured the height of every boy in year 13. So if we're sort of doing a question and in an exam they tell us that sort of information, we need to get in the habit of writing stuff down correctly, formally, in notation. So we start off with a capital letter to define our variable. This should ring bells to what we did in the binomial distribution and the Poisson distribution. Capital letter to define our variable, and here x will be the height of a year 13 boy in centimetres. And the question may say assume that it follows a normal distribution. Well, people's heights generally do if they're taken from a population. You would probably get some short people in year 13, some tall people in year 13, shouldn't be pointing at people now being heightist at the back. Okay? And then average sized people, more of those in the middle. So, the way we write this down is this. X follows that tilde, that little curvy thing we've used before. The normal distribution, we just use an n. When we did the binomial distribution, what sort of came after the b for binomial?
Elements of...
In the brackets with the with n and a p, okay? When the poisson, we had a PO, then a bracket, and what went in the lambda. That's right. For the normal distribution, what goes in is the mean and the variance, not the standard deviation. So, the first number is the mean, the second number is the variance. Which is a bit annoying, really.
Why did you put in the variance when the formula is just this?
It's a very good question. We actually use the standard deviation far more than we do the variance, but the person who invented the normal distribution's formal notation, every textbook anywhere always puts the variance in there. So rather than write it down as 36, which means later on you've actually got square root 36 to work out what the standard deviation is, it's common just to write standard deviation squared in there. Okay? So the key thing, your first red box rule effectively, is you write down x is normal and then it's mu sigma squared that goes in there. Now, what we would have to do in a minute, well, let's try and work out a question in a minute. Let's try and find the height of... I've probably got one here. Let's have a look. We measured Alex. That would be Alex Jones, wouldn't it? Alex Jones we measured last year being 195 centimetres. Since there's no tape measure over here, we'll just go with this again. So we had Alex with 195 centimetres. And what we wanted to do was find the probability that any year 13 boy we chose at random was smaller than Alex. That's the sort of question we were coming at. So the question might be, find the probability a randomly chosen year 13 boy is shorter than Alex. So, if we just think about what we've got, we have got a graph, and it's always useful to do a sketch. A normal curve. Does not have to be beautifully accurate, it's just a sketch. What do we know about it? We know the mean. This graph is always symmetric. The mean, unsurprisingly, is in the middle. So that's 175. Alex's height was over here, 195. So to find the probability that a randomly chosen year 13 boy is shorter than Alex, we want this area here, which is the integral between minus infinity, because this never actually touches the axis, and 195 of that horrible thing we saw earlier. And we don't do it, because it's too horrible to even contemplate doing it. And at that point I'm going to stop this and start another video.